If you've ever tried to assemble a piece of flat-pack furniture, you're familiar with this problem. The diagram shows you where piece A is supposed to go, but the piece in your hand doesn't quite fit the way it should, so either the piece is faulty or the diagram is wrong, and either way, you're not going to be eating off this table tonight. Now imagine that diagram is the standard model of physics that scientists and mathematicians all over the world have worked from for decades, and the piece that won't quite fit is, well, the universe. Specifically, how fast the universe is expanding, something scientists call the Hubble tension. In this episode, we're talking with two experts in cosmology about new developments in efforts to resolve the Hubble tension and why that matters for our understanding of the world we live in. I'm Gemma Ware, and this is The Conversation Weekly, the world explained by experts. I'm joined, first of all, by Lorena Sánchez, Science and Technology Editor at The Conversation in Spain, in Madrid. Thanks very much for being here, Lorena.
Thanks for having me on.
So, Lorena, we're talking today about a wave of excitement that's been rippling through the world of astronomy in recent months. Tell me when you first began hearing about this.
Well, it was something I had my eye on when NASA published data obtained by the James Webb Space Telescope about how fast the universe is expanding. This paper was published in February by Alan Rees, the physicist and Nobel laureate who led the research. And he explained that the new observation from the James Webb Space Telescope matched those obtained years before by the Hubble Space Telescope.
Okay, so why is it such a big deal to confirm something that we already knew years ago?
Yeah, then really at first I didn't understand why confirming something already established could be relevant. But Rees also brought to my attention that something really important was going on. Something that opened up nothing less than the exciting possibility that the experts were misunderstanding the universe.
Why is this such a big deal?
Gemma, this has to do with how we understand the universe. The standard model of cosmology describes the structure of the universe. It is consistent with theories about quantum mechanics, general relativity, and for the most part agrees with current astronomical observation, including the idea that the universe is full of dark matter and dark energy. These things we can't see, but which make up a fundamental part of the cosmos. The Hubble constant is one of the most important numbers in cosmology. It tells us how fast the universe is expanding, and it can be used to determine the age of the universe and its history. But the problem is that previous observations from different scientific teams have obtained different values for the rate at which the universe is expanding today. It is this debate that we refer to as the Hubble tension. The true number could reveal missing pieces in our understanding of physics, like new particles or a new form of dark energy.
And Lorena, I know you've been working with two scholars to help explain what's been going on in this whole debate for The Conversation. One is Bernard Jones. He's an emeritus professor of astronomy at the University of Groningen in the Netherlands. And the other is a former student of his, Vicent J, Martínez, now a professor of astronomy and astrophysics at the University of Valencia in Spain. They've just written a new book with their colleague Virginia Trimble called The Reinvention of Science. And you've known Vicent for a while now, haven't you?
Vicent and I have been friends for years. We have been working together in other fields of science, and so one day he contacted me and wanted to write an in-depth story about the Hubble tension together with the co-author of his book, and they chose The Conversation to do so.
Great. Well, thank you so much, Lorena, for introducing us to them.
Thank you to you, of course.
We set up a call with Vicent and Bernard at Lorena's suggestion. And as we got going, I asked Vicent to help explain to me what scientists actually mean when they say that the universe is expanding.
I have a friend that is not very tall, and he told me, with expansion of the universe, I will grow up. And I say, no, unfortunately, you cannot. I mean, because
Amazing.
Even it does not affect that the single galaxies. Okay, that expansion of the universe is the expansion of the space itself.
I helpful analogy for the expansion of the universe is to imagine baking bread with raisins in it. As the bread cooks, the raisins don't change in size, but the space between them expands as the dough rises. Now imagine this is the universe. The raisins are the galaxies, and they're moving further away from each other as the space between them grows, but the galaxies themselves don't get any bigger. So where did this idea that the universe is expanding come from in the first place? Bernard explained to me that when Albert Einstein first published his general theory of relativity in 1915, scientists realised that this new way of thinking about the universe posed a problem.
The problem Einstein faced was that his force of gravity would have caused any universe you build just simply to collapse on itself, like everything just simply collapses because of the force of gravity.
Several mathematicians postulated that this problem could be solved if it was accepted that the universe is dynamic, meaning it's changing as opposed to static or unchanging. Then, in 1929, the astronomer Edwin Hubble published observations which suggested that the universe could be expanding.
What Hubble was trying to do was to plot that velocity of the galaxies as a function of the distance. For measuring the distances, he was using a tool provided by a Harvard astronomer, Henrietta Leavitt, who showed 10 years before that the way we can measure distances in astronomy could be increased by considering Cepheid stars.
These Cepheids are what are called variable stars, meaning that when observed from Earth, their brightness changes over time. Henrietta Leavitt had observed that fluctuations in the radius of these stars was what caused changes in their brightness. Understanding this gave scientists a way to measure distance in space, and today it constitutes one of the initial rungs on what's known as the cosmic distance ladder, or the local distance ladder. In astronomy, the distances scientists measure are huge. That means that there's no single measurement technique that can be used to calculate both nearer distances, like Earth to the nearest star, and far-off distances, like Earth to the edge of the furthest known galaxy, which incidentally is called Jade's GSZ 140. Instead, scientists create what's called a distance ladder, and each rung on this ladder is a new method of measuring distance. And as the ladder extends, we can measure larger and larger distances in the universe.
And this was the way that Hubble was measuring the distances to the galaxies. He found, for example, variable stars in the galaxy of Andromeda. And by plotting the velocities against the distance, he could find some kind of linear relation. Many people, not Hubble, interpret that as an expansion of the universe, because the farther away was a galaxy, the larger was his velocity.
You heard that right. Edwin Hubble, the man who gave his name to the Hubble constant, which measures how fast the universe is expanding, didn't actually believe himself that the universe was expanding. But in the end, other scientists' interpretation of his data prevailed.
Since then, we have been measuring this quantity, which we call Hubble constant, and that was the beginning of the idea of that the universe was expanding.
Today, there are two primary ways to measure the Hubble constant, which is also called H0.
The first one is basically the one that was used by Edwin Hubble.
Measured this way, the Hubble constant equals the recession velocity of a galaxy. That's measured in kilometers per second, divided by its distance from the observer on Earth, measured in megaparsecs. 1 megaparsec is the distance at which light can travel in approximately 3,860 years. So the Hubble constant is measured in kilometers per second per megaparsec. In the nearly 100 years since Hubble published his equation, our measurements of the velocities and distances in space have become more refined, and so the value of the Hubble constant has evolved quite a bit. What has been the kind of measurement then, using this local distance method for the Hubble constant, in the last decade, say?
At the end of the millennium, more or less, around 2000, it was a key project using the Hubble Space Telescope, led by an astronomer called Wendy Friedman from the Carnegie Institution. And she and her colleagues were able to fix this number around 72, closer to 73. That has not moved too much from that point.
Okay, so it's 73 kilometers per second per megaparsec.
Exactly.
So, Bernard, could I turn to you then to explain, if you could, the other way of measuring the Hubble constant?
Yeah, I've got the difficult way.
Exactly.
That's okay. The other way is done by looking at the cosmic microwave background, which was discovered in 1965. If the universe started with a big bang, it had to be a hot big bang in which all the elements were created. And therefore, the universe and the sky, when you look at it, should be bright because you should see the leftover radiation from this big boom, which occurred 13.8 billion years ago. But because it's actually so hot, we don't see it with our eyeballs. It's way off into the infrared radiation, and it's like you don't see radio waves. You can't even hear them. You've got to build a machine to see them.
These days, cosmologists have a variety of instruments with which to see and measure microwaves in great detail. What they're looking for is a big ball of hot gas from 13.8 billion years ago, when the Big Bang occurred. Now remember that in astrophysics, light has to travel enormous distances to reach Earth. So what we're seeing when we look into a telescope is actually what the universe looked like billions of years ago. The further away something is in distance, the further back in time we're looking. So scientists looking at this cosmic background radiation are hunting around in history for the start of the universe.
Now, the physics of such gas is totally understood since the time of Robert Boyle and Newton and all these eminent people in the 17th century. We know how to calculate the properties of these gases. So by measuring the gas in detail, we can know how hot it was when we're looking at it, what its density was, and by looking at the hydrogen and helium, we can actually say a great deal about the way it's expanding, because at a very early time, the gas is so blazingly hot you can't see through the fire. But the surface of the fire is at about 3,000 degrees. And the reason why the surface disappears is because the density is declined and there's nothing to get in the way. That's the wall of fire that you see. Now, to calculate exactly when that wall of fire happens, which is one of the first calculations I ever did actually, you use the known physics, and that determines how fast it's expanding as well. Hey, how fast? That's the Hubble constant. So the speed of expansion of the universe at a time when it was 1,000 times smaller than it is now, we can actually measure in great gory detail.
When did this second way of measuring the Hubble constant actually come into being?
It started in 1995 with the analysis of the COBE data.
This was data collected from the COBE satellite, the Cosmic Background Explorer, a NASA satellite that operated between 1989 and 1993.
We didn't have enough computing power to do it in 1995, but by 2000 we did.
So we've had this second way of measuring the Hubble constant. What is that current understanding of that measurement? So the other one is 73. What's the one using the cosmic microwave background?
67 roughly. 67.
67. Actually, 67.4 plus or minus 0.5 kilometers per second per megaparsec. So not that far from 73, but definitely not 73. Now, this discrepancy between the two ways of measuring the Hubble constant is what the Hubble tension is all about, and it's been going on for nearly 30 years. During that time, some scientists hypothesized that perhaps the cosmic distance ladder had a weak point. Some doubted the quality of the data from the Hubble Space Telescope, which was used to arrive at that figure 73. Then earlier this year, Adam Rees published that paper which Lorena was telling us about at the beginning of the episode.
This paper by Adam Rees showed that the measurement was completely consistent with the Hubble Space Telescope 2 decades earlier, and certainly using the James Webb, which is one of the largest and fantastic facilities that astronomers have now, they convinced that the measurement of the local ladder continues to be around 73 kilometers per second per megaparsec.
So still a way off the number 67 from the cosmic microwave background method. But then, in April, a few months after Adam Rees published his paper, Wendy Friedman at the University of Chicago released more data from the James Webb Space Telescope. She'd added a few new rungs to the cosmic distance ladder using two other types of stars with predictable luminosities, which are used to measure the expanding universe. And she'd found an H0 of about 69. That's much closer to the 67 calculated using the cosmic microwave background method. Not everyone is convinced that Friedman's new method has resolved the Hubble tension, and she's still working on the calculations too, but all this has caused a flurry of excitement in the world of cosmology. So why is it important that this Hubble tension hasn't been resolved yet, where we are in 2024?
The fundamental basis of science, what distinguishes science from science fiction, is our ability to verify the information we're getting. So when somebody publishes a scientific paper, you don't give them the Nobel Prize right there and then. You wait till somebody else has produced it and got the same answer. This is the key. So when you make a discovery or a first-time measurement, like the temperature of the microwave background, you wait around with bated breath to see, was I measuring the pigeon droppings in my antenna, which is exactly what they were worried about, or was I actually measuring the universe? So you get somebody else who hasn't got pigeon droppings in his antenna to measure it. That happened in Cambridge. And if eventually you all agree, and it's not some kind of confirmation bias, we'll adopt that for the temperature today. So verifiability is the crucial step in all of modern science.
So if I understand what you're saying, the fact that there are these two methods of measuring the rate of the universe expanding and trying to kind of marry them up is important kind of for verifying each method and verifying the way we understand the universe and physics in its totality.
Yes, absolutely.
Okay. Exactly. And the tension is because they are two different.
They refuse to agree with each other.
But what I really want to understand is if one of the methods is proven to be wrong, and like it's actually 73, or the other, I'm not picking one, and it is actually 67, does that fundamentally change our understanding of the universe? Is it like that fundamental?
Yes. It's a great question. I'd say yes, unequivocally.
Yeah, and there is a reason for that. I mean, it's not a matter of which number, because both numbers, as you have said, are already close. But the problem is that we have to understand what happened with the cosmological model. And this is quite important because the cosmological model is the one that we use to interpret our observation of the cosmic microwave background radiation. And with that interpretation, we infer this 67 number, okay? If this is not the case, the model itself has some serious problem.
In other words, based on the standard model of physics, one group of scientists say their telescope observations suggest the Hubble constant right now should be 73. Meanwhile, another group of scientists using the same standard model of physics predict that the Hubble constant should be 67 using cosmic background radiation. It all comes back to the model, whichever way you look at it. So the question is, how wrong is the model? And does it need a drastic reworking or a small tweak?
Something has to be changed in our fundamental understanding. And this implies that probably the idea of the dark energy that we have now, which is rather poor, has to be improved. And that means that, in a sense, the tension is provoking that you still continue doing research and imagine experiments and organizing huge projects with the complicated observation of the cosmos in order to understand what's going on. At the end, this will affect your idea of the whole universe, and probably you will need to change some fundamental ingredient of your cosmological model.
Bernardine Vincent's new book gives many examples of how mysteries like the Hubble tension have played out in the history of science, leading to moments where scientists suddenly realised they had something very wrong all along. One really fascinating example involves the orbit of Mercury around the Sun and how it was calculated based on observations about the planet during the 19th century.
The planet Mercury turns around the Sun, and the point which is closer to the Sun in the elliptic orbit is called the perihelion. And this has a shift that can be calculated using the Newtonian mechanics perfectly.
But towards the end of the 19th century, as telescopes improved and observations became more precise, scientists realised that the calculations using Newton's model were wrong.
And it was again a tension between the observation in this case and the theory.
To explain this problem with the orbit of Mercury, scientists suggested that there was a dark object, an extra planet called Vulcan.
Vulcan was a planet in the inner part of the orbit of Mercury, and that was postulated because it was needed in order to explain these observations. And other people thought about a ring of asteroids or a strange shape of the Sun that should be flatter.
Some people even believed it had to do with an effect of the ether, a mysterious fifth element that has long since been debunked. All of these potential solutions are what Bernard and Vicent's book refers to as dragons, attempts to explain observations that don't match with the prevailing orthodoxy, and which are eventually proven to be myths.
But in that case, the way of solving the puzzle that was the shift of the perihelion of the planet Mercury was not an object. It was needed was a completely change of the theory. And that was where the general theory of the relativity, which is a new theory of gravitation coming out in 1917, was something completely different.
General relativity explained the shift in the orbit of Mercury without any of these convoluted accounts of extra planets or asteroids.
And this could happen, again, in the present context. It could happen that, for example, a new theory of gravity could solve the problem of the dark energy or the dark matter. We have to be open to those ideas. We have to think that in the past, the history of science has proved that sometimes we have to be open in order that new theories could explain what at the present time is not able to explain what we have already.
Right now, scientists are continuing to publish research exploring new methods to calculate the Hubble constant, including measurements of the fluctuations in the density of matter. How this will all turn out is anyone's guess at this point. So either they're going to converge, or there's going to be two very different numbers that are still there.
Right.
And then people need to try kind of playing around with the data and the sources of the data before they actually then go and say, okay, we need a new model.
I like your conclusion, in fact, more than Bernard probably. I think that the ingredients of the model can be modulated. We can make fine-tuning and make that the parameters fix. And this is probably the boring solution, okay? And I must confess that I believe that this should be the solution. But we have to be open that something deeper could be involving within this tension. At the end, we have not only to change the ingredients of the model, but the model itself, which should be based on something that at this moment is completely unknown.
Vicent concluded our conversation with a dark observation that is nevertheless firmly rooted in the history of science.
Planck, the physicist Planck, say that science advances a funeral at a time. That means that you need that people who defend strongly some of the current ideas more or less disappear in order that these ideas get fresh air from the outside.
Yeah, I agree. You've been taught very well, Vicent.
Well, thank you both so much.
Well, thank you. It was a pleasure.
It's been a fascinating discussion. Thank you very much to all of you. I mean, it's exciting. This is a really exciting time, and it's great to share it with you.
That's it for today's episode. Thanks to Lorena Sánchez at The Conversation in Spain, who you heard from at the top of this episode. We'll pop a link in our show notes to an article that she worked on with Vicent, Bernard, and their co-author, Virginia Trimble. And thanks as well to Miriam Frankel, the science editor at The Conversation UK, for her help with this episode. This episode was written and produced by Katie Flood, with production assistance by Mend Marawani. I'm Gemma Ware, the show's executive producer. Sound design was by Eloise Stevens, and our theme music is by Nita Saul. Stephen Kahn is our global executive editor, and Sarai Nandi helps with our transcripts. You can connect with us on Instagram at theconversation.com or email us directly at podcast@theconversation.com. Do sign up for The Conversation's free daily newsletter by clicking on the link in our show notes. If you're enjoying the podcast, please support us and The Conversation more broadly by going to donate.theconversation.com. Please do also rate and review the show wherever you listen. It really helps us reach a wider audience. Thanks so much for listening.